Hi guys, I hope you're having a great day. Please behave for the sub. You know I appreciate that when you do. I know that we have a sheet that looks very similar to this already in our notes, but I really think these logarithmic rules are important, and one way to remember things is to do them again, okay, is the repetition. Now this one has additional rules on it that the other one didn't have, so let's go ahead and fill this in together, okay? Remember, if we have log base b of x times y, if we were to expand that, do you remember what it would look like? Log base b of x plus log base b of y. Okay? The log of a product is equal to the sum of the logs of the arguments. Okay? Next property, log base b of x divided by y. Dividing the arguments is the same as the log base b of x minus log base b of y. So it's this, the log of the quotient is equal to the difference of the logs of the arguments. Okay? Log base b of x raised to the p power. The log of a number raised to a power is the same as the power times the log of the argument. So this is where we would take that exponent and bring it down in front as a multiplier. So p log base b of x. Okay? Those are three of the ones that we've really focused on and concentrated on. Okay? These other three down here are just really good to know. Okay? You can get to the first two with this one. We might as well make it a little easier on ourselves. Okay? Log base b of b raised to the p power. Well, if we use the property that we used back there, we know we bring this around in front, but because of this property right here, we know that log base b of b is 1. So if we have log base b of b to the p power, that's just p. Okay? So for an example, if we have log base 2 of 2 to the 6th power, then x equals 6. Okay? The log base and the argument, if the log base and the argument are the same, it's always equal to the power. Right? It's really the same rule here, isn't it? Okay? Log base 2 of 2 is 1. The base and the argument are the same, so that x value is 1. If the log base and the argument are the same, it's always equal to the understood power of 1. Okay? The last one is the one that we worked on the end of last week, log base b of n. Okay, this is the change of base formula, the change of base property, and this is going to be equal to the log base 10 of n divided by the log base 10 of b. Okay, now somebody asked me last week, why does it have to be 10? Why couldn't it be like 4? And in all honesty, it could be 4. It could be log base 4 of n divided by log base 4 of b. But if you'll remember, why do we have the change of base property? We have the change of base property because those old calculators couldn't do any other base besides 10 or e. So that's why we choose to make this base 10. Okay? So if we're going to rewrite this as log base 10, or if we're going to use the change of base formula, this would be log of 32 divided by the log of 4. Now, why didn't I write the 10 right here like I did over here? Do you remember? Log base 10 is the common log. If there's not a base written, it's understood to be 10. Okay? We could actually put this into our calculator. We could say log of 32 divided by log, when I do that, divided by log of 4. Oh, great. Log of 4 equals 2.5. Okay? How would I rewrite this problem when it has variables in it? Okay? We'd still say log of x plus 1 divided by log of 2. But this time we couldn't simplify it any further. That would probably be something we would graph. See how it even has f of x at the front? Okay? To solve for the change of base property. All right? The other worksheet that I have for you to do today is called Exponential Equations Plug and Solve. Okay? Read about each situation, decide whether each question requires you to evaluate or solve the given function. In every case, show the steps that lead to your answer. All right? So the first question asks about a piece of paper. Okay? I guess it really tells you about a piece of paper first. A piece of paper is about 0.004, so 10 hundredths, thousandths, 4 thousandths inches thick. If you fold the paper in half, the stack is 0.008 or 8 thousandths inches thick. If you fold it in half again, it would be 16 thousandths inches thick, and so forth. The equation to model the thickness of the stack of paper of x folds is given. Okay? Now, you guys did something at the very beginning of this chapter, exploration about exponents and logarithms with paper, didn't you? Okay? So this is kind of bringing that back to you. So determine the thickness of the paper after 8 folds. Okay? Well, all that takes is, we know that the number of folds is x, and if we know we have 8 folds, we just want to take 0.004 times 2 raised to the 8th power. And we get an answer of 1.024. Oh, but what did we do? Because it does tell you at the very top, show the steps that lead to your answer. Okay, so we want to say t of 8 equals 0.004 times 2 to the 8th power. And that answer is 1.024. Okay, now this is a word problem. This number right here is not just a number, it has a meaning. Okay, so what are we going to label this? Inches. Okay? Any questions so far? I mean, not that I could answer any, but think about them in your head. You can ask them tomorrow. B. Set up and solve an equation to determine about how many folds it would require to make a stack 11 feet tall. Okay? So they're like, hint, 11 feet is how many inches? So they want you to be really careful here, because the original problem is giving in inches, and this is very clearly giving you feet. Okay, so the first thing we have to do is 11 times 12, so we know how many inches that is, and you realize that's 132 inches. Okay, so start with the equation. Let me scoot that down just a little bit. Start with the equation that we're given, except this time we know the thickness. We know it's 132 inches. And that's going to equal 0.004 times 2 to the x power. So if we're solving this, then the first thing we do is divide both sides by 0.004. So 132 divided by 0.004, 33,000 equals 2 to the x power. When that exponent is when that variable is in the exponent, that's when we want to use our logarithms. Okay, so if we rewrite this in logarithmic form, we have log base 2 of 33,000 equals x. And since we are fortunate enough to have a calculator that will do the logarithm for me of base 2, we're going to go ahead and let it. Log base 2 of 33,000 equals 15.0102, and we're talking realistically, we're asking how many folds. Okay, so then we would get x equals approximately 15 folds. Okay, now I still want you to keep this in the back of your head, because if we weren't fortunate enough to have a calculator that would do log base 2, I want you to know that you could do log of 33,000 divided by log of 2. Not there. 2. Guess what we get? The same exact thing. Okay? Look at problem number 4, please. Scientists raise fruit flies in a lab. While they started off with a few flies, the population increased rapidly at first. The equation to estimate the population of flies, F, is given, where W is the time in weeks. So how many flies did the scientists start with? Okay, a couple ways to figure this out. We could take this equation. If we know that time in weeks, when did they start? Well, they started when weeks was 0. Okay, so we could take a 0 and plug that in there. Something times 0 is 0. Anything to the 0 power is 1. 450 times 1 is 1. 500 minus 450 is 50. Okay? Please keep in mind, though, that we have really nice calculators that will allow us to skip some of this arithmetic. What if we went to a graph and put that equation in? The graph isn't so much as important to me as the table. So we go to Control T. Look what happens when x is 0, 50. We got the same thing. Okay? So they started with 50 flies. Well, if we're showing our work, we looked at the table in the calculator where x equals 0. Let's do that. Okay? That's our work. That's what we did. All right? How long did it take for the population to reach 400 flies? Well, we have a couple choices again. Once again, that 400 is, that's not the weeks, that's the population, that's the f of w. So we could actually say 400 equals 500 minus 450 times 2.71828 raised to the negative 0.3 w. Okay, we could do that. We could scroll until we get to 400. The problem is it doesn't get to exactly 400, does it? Okay, so different ways to think. We could go to the graph and find out where y is 400. Probably for us, the easiest way is the algebraic way. Okay, so we would take this equation here and we would solve it. Okay, we would subtract 500 from both sides first. Negative 100 equals negative 450 times 2.71828 raised to the negative 0.3 w power. We would divide both sides by negative 450. Negative 100 divided by negative 450. 2/9. Okay? 2/9 equals 2.71828, negative 0.3 w. Now, some of you are going to realize pretty quickly that I don't like that because this is in decimals and that's in fractions. So we could say 2 divided by 9, Control Enter to get the decimal, and that's why they didn't give it to the decimal in the first place, because it's not exact, it's a rounded number. Okay? So from here, we would go ahead and write it in it's in exponential form. We'd write it in logarithmic form. So we'd say log base 2.71828 of 2/9 equals negative 0.3 w. So when we take the log base 2.71828 of, give myself a fraction, 2/9, that gives me that number, negative 1.50408, negative 1.50408, which equals negative 0.3 w. And to actually go ahead and do that last step to solve for the w, I divide both sides by negative 0.3, divided by negative 0.3, 5.01359. So 5.01 weeks. Okay? Now, if I look back at my graph, could I have told that it was somewhere near 5? If we're looking for when it's equal to 400, which is what we were looking for, right? 399 is pretty close to 400. Okay? But it wanted an exact value. We got pretty close. Okay? So that's the answer for B. I know that you don't have very much room on this paper, because I didn't have enough room on this paper, which is why I grabbed some scratch paper. I'm going to make sure I keep my scratch paper with my work. Okay? How big was the population after 20 weeks and after 40 weeks? Well, weeks is W. Okay? So this would be a great time to use the technology we have at our disposal to go scroll down to 20. So f of 20 was 498.885. We also need f of 40. Scrolling. 49. Whoa. 499.997. So after 20 weeks, they have 498-ish flies. And after 40 weeks, 499-ish flies. How is that possible? Explain. Well, we can't really see the graph very well. What if I changed my window? Okay, let's change my window. Trying to get it where you can see it. Change my window settings. My y values are like 500 and stuff. Okay, so we're talking about 20 and 40 weeks, so let's start at -1, only just so we can see the axis, because we can't really have -1 weeks. And let's go to 50 weeks. For my y minimum, we'll start at 0. Oh, or we could start at 50, because that's where they started, right? 50. And then let's go ahead to 550, just so we can see everything. What's happening here? Increases super fast at the beginning, and then what happens? That's the asymptote. That's the limit of the population that they can sustain. So we have an asymptote at, where do you think it's at? Where is it getting closer and closer to? We could go back to the table and look and scroll back down to where we were, maybe. Just as it scrolls, where are the numbers getting closer and closer to? Oh, look at that. The calculator didn't even have the capacity to stop giving values, to keep rounding. So it's at 500. So that's something we have to be careful of. The calculator doesn't even have the capacity to get closer and closer to that. Okay? So our limit's there at 500. All right? Please do the rest of this worksheet, the 2 on the front and then the 4 on the back, and I will check those when I get back tomorrow. I hope you have a wonderful day.